we're recording now, and this is for your fellow students, classmates, to see the solutions for the midterm. Let me quickly do some adjustments here. All right, do you guys have midterm problems in front of you? Pull up midterm problems so that we'll all see what we're talking about. And I don't need to sort of use them a screen to.
Are they posted?
Right, you don't have them. Okay. That's a bit of a problem. I guess I'll just write them down while we're going. Let me just push something off my iPad and have it on my screen, and so that I can use my iPad for writing down stuff and you could see it. Okay, good. Right. All right, so now we can start. Okay, just a second. Okay, so share screen. So the first problem was particle in a box, and we had a wave function phi of x. First problem, phi of x equals to x squared, x minus L. That's inside the box. Outside the box, it's 0. And there are a few integrals given, and you were asked first about normalization, right? So 1, normalization. So does anyone have problems with that? So how do we normalize this function? We take the integral from 0 to L, phi of x, don't forget the square, dx, that would be normalization factor with a n square, right? And then once we obtain this not equal to 1, we will be able to take the normalized function as essentially phi x divided by n, right? Or phi x divided by square root of this integral. Right? So we just need to do the integral and then take a square root of it and divide the function by that. All right, so let's do it. And x squared, x minus L, you need to square. Absolute square is the same as it's just a square because it's a real function, right? So it's x fourth, x minus L squared. And that's here that some people already somehow made a mistake by not squaring correctly. And so we have x fourth, x squared minus 2xl plus L squared, right? So the decomposition, and then it's x to the 6 minus 2x to the 5 L plus x to the 4 L square, right? So that's the function which we need now to integrate between 0 and L, and plus x to the 4 L square dx. You all know how to integrate polynomial. That becomes x to the 7 divided by 7 minus 2 divided by the 6 x to the 6 L plus x to the 5 divided by 5 L square. Right, so, and this is between 0 and L. 0 is not important. What is important is L, and you have L to the 7 everywhere because you could see. So ends up being 7 power of L. And you have 1 over 7 in the first term, minus 1 over 3 in the second term, plus 1 over 5 in the third term. And so then it's just a simple arithmetics of nature, not natural, but rational numbers. It turns out to be L7, 105. And 105 comes from 7 times 3 times 5, because 7 times 3 is 21, times 5 is 105, right? And any questions about that?
All
So,
good.
yeah, all good. So then you could first see that for general L, this is not 1, right? So then f of x normalized is x squared x minus L. And then we need to divide by this number squared, and that would be 105 L to the 7th, right? So that's the normalized function. Okay. Now we gonna go and solve for second problem within the first one. So it's 1, 2. So 1, 2 is asking whether this is a solution of time-dependent Schrodinger equation. If in initial state x0, it's phi of x, normalized, because, well, if we want to represent the physical system, then we need to normalize, and then well, it is a solution of time-dependent Schrodinger equation because it doesn't violate any boundary conditions, and at initial time, function can be anything that doesn't violate boundary condition. So that's where we start. Now, how do we need to? Yeah, I guess the next question is that how do we essentially reduce the psi at xt? Now, the idea here is that in order to produce the solutions of the time-dependent Schrodinger equation, we need to express, the easiest way is just to express this as a linear combination of eigenstates, right, of the particle in the box, because we're talking about being in the box, right? And then once we produce this decomposition where CNs are integrals of phi n x with psi n, psi with small n, x dx 0L. Once we have that, we can simply see that psi of xt equals that decomposition. Cn's are coming from here, psi n's are given, or you remember them, and then you can kind of h bar minus 1 et. You could skip the h bar if you want, assuming atomic units, right? So, and in order to check that indeed this is the solution, then you could simply check that psi of xt in this form is the same as a IH bar d over dt psi xt. So you calculate this, and then you calculate this. That was the idea. So h psi applied to Cn psi n exponent. Oh, let's okay, we keep the h bar for the completeness minus I E n t divided by h bar, and it's equal to essentially h is linear operator that acts on the psi n everywhere because it's acting on the coordinate function psi n's, and every time it acts on them, it will produce En psi n. So the solution will be well, left-hand side will be En with coefficients, and then psi n, of course, and then there's this exponent En t divided by h bar. So that's our left-hand side, and the right-hand side, we need to differentiate IH bar d over dt, the same sum with psi n. Right? And every time we differentiate, differentiation acts on the exponent only, or exponential function only, because neither coefficient nor a wave function is time dependent, so they're like constants in time. And so we have IH bar sum over n Cn psi n, and here when we differentiate with respect to t, we get minus E n I divided by h bar, and the exponent. Okay, so then we need to do some cancellations. H bar minus I times I gives you identity, so you can just cross them. And the result will be sum over Cn psi n En's exponent of minus I En t divided by h bar. That's our right-hand side. And you can check that now left-hand side and right-hand side are the same. So that simply means that this form is a solution of time-dependent Schrodinger equation. And in order to sort of go from the psi 0, we just need to find the coefficients in order to get to this form. Okay, any questions regarding this show or demonstration?
Nope.
Okay, so then this is I guess the check that it's 1.2 and this one was 1.3. Check that psi xt is a solution. And then the fourth question, 1.4, question is phi x. Is it a solution of time-independent Schrodinger equation? Time-independent Schrodinger equation is this. The question is whether that's the case. And you could ideally just apply the Hamiltonian, because it's not given, but supposedly you already know that it's just kinetic energy applied to psi x, and the second derivative gives you constant that is +2, right? Since it's no, actually in this case it's not that simple. I'm thinking about the different function, so we could actually do this. So second derivative acting on the function, it's gonna be minus h bar squared to m, and double differentiation of x cube gives you 3 times 2 times x, and double differentiation of minus l multiplied by x2 is gonna give you minus 2l. That's the function. with a constant. And so this is not the same as energy times some constant multiplied by x squared, x minus L, right? So that is not the case, and therefore the answer is no. It's not it's not the solution for time-independent Schrodinger equation. Any questions? So some people just say no, yes, that's kind of not enough because I don't know. There's a 50% chance that you're gonna get it accidentally right if you say yes or no. So therefore, for getting full score, you need really to show it that you understand what you're saying. Number 1.5, suggest an alternative for phi x so that the answer to the previous question will be different. The alternative phi x should be alternative phi x should be one of the psi n x, which is square root of 2 over L sine n pi x divided by L, right? So it's given. You could choose n anything from 1 to any finite number. So that will be solution for time-independent Schrodinger equation. We got this during lectures. Suggest alternative for, okay, that's 1.5, 1.6. If we measure the energy of a particle in the state phi x, what would be the results? So phi x, since it's not an eigenfunction, if we measure it, it will collapse to various eigen values of the Hamiltonian. They're given, but the probabilities are coefficients squared, right? So it's not a single energy, it's multiple energies, and they depend on this probabilities depends on the coefficients. That's as much as we can say about this experiment. Any questions?
Nope.
All right, 1.7. What are the probabilities to get the results you reported in the previous question? These are probabilities, and now we need to really calculate the coefficients, Cn's. So Cn's is that integral that we wrote here. Don't forget that the function needs to be normalized so that the coefficients would make, like when you square them, there will be probabilities, because if the function is not normalized, coefficients squares, some of them could be more than 1, and that's that sort of makes them not a good probabilities. So you calculate Cn's, and the calculation of Cn's requires taking the integral of 0 to L sine of some ax function, where a is n pi divided by L. Just for short notation, I keep it a here, multiply by x cubed minus Lx squared dx, right? So that's the integral that you need to take. And two parts of that integral were given. Well, times some constants here, of course. You need to have some constants, like for the sine of ax, have a constant 2 over L. And for this guy, you have a constant which is, well, let's say divided by L to the 7, 105, right? So that's another constant that one needs to take into account. And after, I'm not going to go through the entire kind of bookkeeping of what sort of needs to be done here, because the algebra, like, you just need to be careful with the terms, and all the terms are given. So what I get at the end is 2 to the L times L to the 3 divided by n pi cube plus 4L cube divided by n pi cube cosine of n pi. And the cosine of n pi is -1 into the power of n. because if n is 0, cosine is 1. If n is 2, then cosine is, sorry, if n is 1 after 0, 1, then cosine of pi is going to be -1, right? And so on. So this is -1 into the power of n. And the final formula then becomes 2 to the L to the 4th n pi cube 1 plus -1 into the power of 2 n times 2. So that's what you get, and that's the Cn. And then Cn square will be the probabilities. Any questions here?
Nope.
All right, good. So now 1.8. The question 1.8, will these probabilities change with time? They won't, because, well, technically one could say that the coefficients in the solution of Schrödinger equation is, well, let me write it down just carefully. So technically, psi of xt is a sum over n Cn exponent of Ent divided h bar phi n, sorry, psi n x, right? So these are the coefficients that we need to square to get the probabilities at later time, and they are the same as Cn squares, so constant in time. Okay, so most of the people, I think, answer that correctly. What is the average momentum and energy of the particle in phi x? Right, so that's 1.9. So the momentum is just an integral of phi x with the momentum operator, again between 0 and L. And that is 0 because momentum of any real function is 0. It's shown in one of the YouTube lectures, and we could just do it thinking about the fact that okay, this is the expectation value, that's the average, right? And then what happens here is that momentum is minus I h bar d over dx, right? So you can take minus I outside of the integral, and what you have as an integral is like yeah, let me quickly fix this. So as the integral, you have phi of x dx. So if the integral of the real functions is real, then the only way we can get real number multiplied by I to be real, it's when this number is 0, right? Because we know that the expectation value of the Hermitian operator, it needs to be real. That's one way to show that it should be 0. Another is we could simply do the integration by parts for this integral and see that okay, the boundary conditions are zeros essentially, and we can get yeah, our 0 that way by taking the integral. Any questions about that part?
Nope.
All right, so then kinetic energy with a normalized function. Wait, yeah, that's the second part of this question. What is the average kinetic energy or energy? Because the only energy here is kinetic energy. So we need to take this integral, and first we differentiate, and then let's say we differentiate, we get this function, and then we need to do the integral or differentiate function with the original one. And the idea is to not to forget the normalization. So this is our normalization. And then the integral of x to the square L minus x multiplied by doubly differentiated. We somewhere did this already. Or let me just simply write what what I have. It is this times minus h bar squared 2m times 2 times 3x minus L. So that's after differentiation. And let's simplify the constant and move it away. 105 L to the 7 multiplied by h squared m. And the integral will be between x squared, L minus x, 3x minus L, dx equals 2. And that integral, if you do it correctly between 0 and L, will simply be minus L to the fifth 15 over 15. It's a little bit, I guess, tedious to calculate, so I'll just say what it is. But in reality, it's just 4 terms here. Yeah, 4 terms you can integrate, and they're all sort of powers of x, easy to integrate. And then after doing all the cancellation of constants, because 105 is 3 times 5 times 7, and 15 is 3 times 5. So you have a lot of cancellation, which gives you 7h bar squared divided by ml squared. That's the answer. You could compare that answer with well, ground state, right? Because nothing can be lower than ground state, and this should be more than the ground state. And the ground state is h bar squared, pi squared, n squared over 2ml squared, right? So then the question here is that if n equals 1, right? So n squared is not present practically, then pi squared over 2, whether it's smaller than 7. Pi squared is roughly 9, over 2 is about 4.5. So we have 7 here, 4.5 in the ground state. Indeed, we got a result that is in accord with the variational theorem, right? Because no function can give an expectation value of energy larger than, smaller than the ground state. For the same reason, this needs to be negative, because to cancel this negative in h squared. Any questions? You see here, the important parts from knowing all this, like variational theorem, is that you can check your calculations, right? So, because sometimes we all make mistakes, and knowing what the result should be roughly in what range, that helps to avoid those mistakes. Any questions?
No.
All right, cool. Then, okay, we solved 9, the 10, 110. Essentially, this is most of the people solve properly. That is the first A it's not a good solution. It's not a good wave function because effectively x squared minus L squared. It's not zero at x equals 0. But some people miss that x squared is x minus L and x plus L. And then when they were doing the suggestion, I think it was, suggestion in the item D, the question was, give your example of a function that is unsuitable function. And they were given the same function as an A. Well, I couldn't give you a full point for that because simply, well, you're given the same function that you already given in A. You just don't see it because you have poor knowledge of algebra. Now, the D item needs to be different, and it could be as simple as just x, right? Because x is not a good function. It doesn't satisfy boundary conditions. Now, C, what is a good function? You could just say an eigenstate, psi n. And then the B was also not a good function because it's x plus L divided by x minus L. There's still a problem when, let's say, x equals L. And at 0 as well, right? So both are problematic. All right. But this problem, the 10th, is sort of the easiest of all. Everyone more or less did it well. So problem 2, which is a variational approach. Okay, so the first one was describe how can you find an approximation to the ground state. Just formulate in words, what would you do? Essentially, what needs to be done here is to formulate, okay, what I do is I take the function, I put it in the energy functional, which is a function t plus v function divided by this. And because the function has a dependence on L, that means that the energy functional will also have a dependence on L. And then to find the L optimal, I will solve the equation dE over dL equals to 0. And after solving this, we get the L optimal, and we'll get essentially phi L optimal. That works because the energy of the phi L optimal is always bigger or equal than the true minimal, as the ground state energy. Okay, so that's pretty much the description of variational approach. Some people just start copying whatever was part of the lecture, which shows not a clear understanding of what's going on here. Okay, so then you also can have this picture in mind that there's a box, essentially. Yeah, the box between 0 and L. And there is a quadratic potential. Okay. And then let us find the average kinetic energy. So it's a sort of function, quadratic 0L. And then there is a kx squared potential. Now, let's find the sort of t. That's a second problem, right? So t is a function of L. And what helps is to get the, because we will need the psi of L normalization. Let's do the normalization. First, x squared L minus x, the same way we did it before. Now different power, and we get 30 over L to the fifth. The other way around with -1. So that's the n square factor. And then in order to get the sort of, well, we don't need to really normalize function because we have a task to find the T of L. And we could just divide by this, right? We could divide by L to the fifth divided by 30. Now we need to find f phi L T phi L. And this is, again, integral. You take the phi L of x and apply differential operator to phi L of x dx. And what we get is essentially the integral of, let me see, where is my, right here. Yeah. What we get is h bar square divided by m. This division by L530 minus 1. And here we have an integral of x L minus x dx. So the 2m here disappeared because there was a 2 here when we differentiate the function. So then the answer becomes, if you do this integration, then it's the third power of L that you get. And here you have h bar squared m 30 divided by L to the fifth. And here you have x square L minus x 0 to L, x cube here divided by 2, here divided by 3, x cube 0 to L. And the final result is, after doing all this algebra, h squared L to the third 6m times 30 divided by L to the fifth. And this is h squared times 5 divided by m times 1 over L squared. So that's the answer for kinetic energy. Okay?
Okay.
Good. So now let's say 2.3, we need the potential energy. And before we go to potential energy, again, how do we check the result is correct? Well, first of all, it needs to be positive. Second, the smaller the L, the larger the kinetic energy should be. We talked about that in the lecture because you're squeezing and the kinetic energy is growing. Right? So that kind of dependence on the L squared in the denominator, that's the right dependence. All right. Now let's do V of L averaged. It's the integral again between 0 and L. So that's where the function is kx squared. And then two functions, x L minus x squared divided by 2 dx, right? And then we need this n to the, how do you define? We need n to the minus 2 for the normalization, right? And this can be essentially just integrated. It's not that complicated if you do keep track of all the powers, and k over 2 times n to the minus 2, 0 and L. We have effectively x to the 4, L minus x squared. Oops. L minus x all this squared dx. And if you open this up, you're gonna get k over 2 n minus 2 x to the 5th 5 L squared minus 2x 6 L plus x to the 7th divided by 7 from 0 to L. So essentially the integral you get here is the same as the integral you got in the first problem when you normalized. Okay, so you could just reuse that integral value. And we know what that is if you do all the kind of terms correctly and do all the cancellation, you're going to get KL squared divided by 7. That's potential energy. And I guess I didn't finish the picture here, so let me be sort of careful in my notation. So we have axis here, 0, L, and function is like this. Oops. Function is like this, and the potential is quadratic, right? So in that sense, we have clearly not the eigenstate, but something that is off the center, right? So one can do the problem with a different function, which is more in the center, and it will be having a lower energy. But we have this essentially potential energy as a function of L. And this is the kinetic energy as a function of L. And now the question is, what is L optimal? That's the number 4. And how do we obtain it? We kind of first do the E as a function of L, which is KL squared divided by 7 plus 5 H bar squared divided by L squared M. Right, so that's our function. And clearly this part wants the L to be smaller, this part wants L to be larger. And so there is some optimality condition, dE over L equals to, we take the derivative, 2k times L divided by 7 minus 2 5h bar squared divided by ml cubed. So that's our equation, equals to 0. And then we find in that KL over 7 equals to 5h bar squared ml cube, right? And then this gives us L to the 4th equals 5h squared 7 over k divided by m. And L optimal is square root of the 4th power, 35 h bar squared divided by k times m. So that's our L optimal. Energy optimal is then just putting this inside, and we're gonna get k over 7. Sorry, not L, 7. 35 h bar squared km 1/2 because L was squared there, plus 5h bar squared m times square root of km divided by 45h squared. And the answer becomes actually quite nice. You have h over 5/7 times the square root of k over m in the first term, and the same in the second term. Okay, so, and the total energy h bar omega, because this is omegas, h bar omega multiplied by 2 square root of 5 divided by 7. And the ground state energy is h bar omega divided by 2. We clearly have more than we clearly have more than 1/2, right? So this is more what we call then ground state, which is in accord again with the variational theorem. Any questions?
No.
So, okay, so then great. So that concludes the solutions. I'll post this notes on the Quarkus, and I'll see you on Monday then.
See you on Monday.
Bye-bye.